Hello class, good day to everyone. Welcome to our discussion. Actually, this is the second version of the same video, which you find out there was no audio. So let's try this time, hoping that the audio will be heard this time. Alright, so before we begin, let us have the objectives of our discussion for today. So at the end of our discussions, you should be able to understand the basic concepts of partial derivatives, identify the different notations of partial derivatives, and apply the understood concepts into solving basic problems in finding the partial derivative of the given function of two or more variables. So for the basic concept, in this part of our lessons, we will develop the mathematical tools for studying rates of change that involve two or more independent variables. So partial derivatives of functions of two variables. If z is a function of two variables, x and y, then one can inquire how the value of z changes if y is held fixed or constant and x is allowed to vary, or if x is held fixed or constant and y is allowed to vary. For example, the ideal gas in physics states that under appropriate conditions, the pressure exerted by a gas is a function of the volume of the gas and its temperature. Thus, physicists studying gases might be interested in the rate of change of the pressure if the volume is held fixed or constant and the temperature is allowed to vary, or if the temperature is held fixed or constant and the volume is allowed to vary. So we now define a derivative that describes such rates of change. Suppose that x sub 0, y sub 0 is the coordinates of a point in the domain of a function f of x and y. If we fix y and we let that y equal to y sub o, then f sub x and y sub 0 is a function of the variable x alone. So the value of the derivative given in this notation, the value of the derivative given uh, in this notation, derivative of f sub x and y sub 0 with respect to x at x sub 0 then gives us a measure of the instantaneous rate of change of f with respect to x at the point with coordinates x sub 0, y sub 0. Similarly, the value of the derivative given in this notation, derivative of f sub x sub 0, y, with respect to y, at y sub 0, give us a measure of the instantaneous rate of change of f with respect to y at the point coordinates x sub 0, y sub 0. So these derivatives are so basic to the study of the differential calculus of multivariable functions that they have their own name and notation. So for our definitions, we have if z equal to f sub x and y, and x sub 0, y sub 0 is a point in the domain of f, then the partial derivative of f with respect to x at this point with the coordinates x sub 0, y sub 0, also called the partial derivative of z with respect to x at this point with coordinates x sub 0, y sub 0, is the derivative at x sub 0 of the function that result when y equal to y sub o. So it means that we held y as constant or fixed, and x is allowed to vary. So this partial derivatives is denoted by this uh, f sub x of x sub 0, y sub 0, which is equivalent to this notation. So derivative of the function of x and y sub 0 with respect to x, x equal to x sub 0, and this is equal to the limit of the function of x sub 0 plus delta x y sub 0 minus f sub x sub 0 y sub 0 divided by delta x as delta x approaches to 0. Okay, so look familiar. So the same as in our function of a single variable. So there's a little uh, minor difference here on this part. Similarly, the partial derivative of f with respect to y at this point with coordinates x sub 0, y sub 0, also called the partial derivative of z with respect to y at this point with coordinates x sub 0, y sub 0, is the derivative at y sub 0 of the function that result when x is held constant or x is held fixed, that is equal to x sub 0, and y is allowed to vary. So this partial derivative is denoted by this f sub y of x sub 0, y sub 0, and is given by this expression. So f sub y x sub y of x sub 0, y sub 0 equal to the derivative of x sub 0 y with respect to y, where y is equal to y sub 0. It means that we held here x as constant, and it is equivalent to the limit of the function of x sub 0, y sub 0 plus delta y minus f sub x sub 0, y sub 0 divided by delta y as delta y approaches to 0. Okay, so these are the two important definitions, class, that we need to remember and also understand. All right? So the limits of 1 and 2, it means the limits of this definition number 1 and definition number 2 show the relationship between partial derivatives and the derivatives of functions of one variable. In practice, our usual method for computing partial derivatives is to hold one variable fixed or constant and then differentiate the resulting function using the derivative rules for functions of one variable. Okay, so it means, class, that we still need to use the rules in differentiation that you had learned before, okay, when we do partial differentiation. So for example, if you're given this problem, find f of x, means the partial derivative of the function with respect to x at this point. So in our definition, class, this is our x sub 0, this is our y sub 0, and f sub y, meaning that the partial derivative of the function with respect to y, also at the same point with coordinates 1 and 3, where 1 is our x sub 0, this is our y sub 0, for the function of x and y equal to 2x cubed y squared plus 2y plus 4x. So our solution here, so we if we find the partial derivative of the function with respect to x, so we have here the subscript as x, no? F sub x. So it means that we are differentiating the given function of two variables with respect to x. So you see here the first part here, we have x. It means that we x is our we're differentiating the function with respect to x, and we're using y or holding y as constant. Okay, so this expression is equivalent to this one. So it means that the derivative of this function with respect to x, so they are just the same, class. They have the same meaning. So this is equal to, so we are now taking the derivative of the function. So here, you might wonder why it becomes 18, where are y? So where's the y now? So this becomes 18, class, because we have here y. We substitute y because we hold y or held y constant. So our y here, as given in the problem, this is equal to 3. So y here, we substitute y here equal to 3. So 3 squared, 9. Right? 3 squared, 9 times 2, 18. So that's why we have 18 here. 18 times x squared. So the first term here becomes 18x squared because we substitute the value of y here, which is equal to 3. Then 2 times y. Y is 3. So 2 times 3 is equal to 6. So we have here 6. Then we have 4x. So we just copy 4x and we just rearrange it. Okay? Equal to. So this time you apply the rules in differentiation. So you take the derivative of this part. So we have a power rule. This is a constant, then times the variable with a power or exponent. So applying the uh, constant and variable with exponent here. So you apply the power rule. So this becomes, when you differentiate this one, so 3 will go down. So 3 times 18 is 54. Then the power here is minus 1. So that becomes x squared plus 4 times the derivative of x with respect to x is equal to 1. So 4 times 1 equal to 4. And the derivative of 6 is equal to 0. So that's why we have here the partial derivative of the given function equal to 54 x squared plus 4. We have f sub, we solve now the value of the partial derivative of at this point. So substituting the values, so 54, so here this is, you just multiply here. So we have 54. Okay, so our x is equal to 1 as given in the problem. Okay, so x is equal to 1, x sub 0, so multiplied by 1, and then so this is squared, then plus 4. Okay, so 1 squared is equal to 1 times 54 equal to 54 plus 4. So this is equal to 58. Okay, so this is 58. So this is just the same as what we have here. Okay, now solving for the partial derivative of the given function with respect to y. All right, so this is now our notation now, and this is equivalent to this notation. Okay, and this time we have x. For this part class, we are differentiating the function with respect to y. So we held x as constant. So we use the value of x here, and our y is variable. Okay, so differentiating. So we have 2y squared. So y it becomes 2y squared. So again, we go back to the given here. So looking at the given, so now we held x as constant for the second part. So it means if x is constant, so we use the value of x here that is equal to 1. So you substitute the value of x here which is equal to 1. So 2 times 1, 1 cube is 1 times 2 is 2 times y squared, so 2y squared. So that's why you have here 2y squared. Okay, then 2y, so you just copy 2y. Then 4 times x is equal to 1. Okay, so x here is equal to 1. Sorry, here x is equal to 1. So 4 times 1 is equal to 4. So that's why we have here 4. Okay, and then that's the time you differentiate using the normal differentiation. Okay, so this is the term now that we are going to differentiate using the rules that we have learned before. So derivative of this, you apply power rule. So we have 2 will go down. So 2 times 2, 4. Power is 2 minus 1, so equal to 1. So that's why you have here 4 times y. Plus derivative of 2y is equal to 2 times derivative of y with respect to y. So this becomes 2. Then derivative of a constant, which is 4, equal to 0. So that's why we have here the result 4y plus 2. So substituting the value so that we can solve for the value of the partial derivative. No? 4 times y is equal to, so our y here is given as 3. Okay, so 4 times 3, then plus 2. So 4 times 3 is 12, then plus 2. So this is equal to 14. Okay, so this is the answer, which is this one. Okay, so that's how easy class, no? This topic is. Alright, so I hope you were able to follow the steps on how to solve this problem, partial derivatives. So let's go to the next concept. So formula 1 and 2, or definition 1 and 2, define the partial derivative of a function at a specific point. Okay, point with the coordinates x sub 0 and y sub 0. However, often it will be desirable to omit the subscripts and think of the partial derivatives as function of the variables x and y. So these functions are uh, given in this formula. F sub the partial derivative of x and y with respect to x is equal to the limit of f of x plus delta x y minus f sub x and y divided by delta x as delta x approaches to 0. And the other one, partial derivative of the function with respect to y of the function of x and y equal to the limit of f of x y plus delta y minus f sub xy divided by delta y as delta y approaches to 0. So the following example gives an alternative way of performing the computations in example number 1. So in this case, class, let us solve the same problem, but this time using this concept here. Okay, so example number 2, we're given the same problem as in our example number 1. So here, using this notation, so we have for our solution, keeping y fixed and differentiating with respect to x. So meaning y is fixed, meaning we let y a constant. We let y or treat the variable y as constant, and then we differentiate with respect to x. So it yields something like this. So using this notation, okay, so this part here. So the partial derivative of the function of x and y with respect to x is equal to the derivative of the function, okay, with respect to x equal to, so in this case, class, since y is constant, okay, so since we treat y as constant, okay, so y is constant. So what we are going to do here when we differentiate this partially, so we treat y as constant, so we isolate 2 and y squared. Okay, so isolating 2 and y squared because they are constants, so you just take the derivative of this x cube. Okay, so take the derivative of this x cube using the power rule. So the power rule will go down. Okay, so this becomes 3x squared, right? So that becomes 3x squared. Okay, and then you multiply this 3x squared with 2 and y squared. So 2 times 3, that is 6 times x squared, so x squared times y squared. So that's why we have here 6x squared y squared. Then plus, so y is constant, 2 times y, so the product is constant, so derivative of constant is equal to 0. So that's why you cannot see this anymore here. But for the third term, so the third term is derivative of 4x. So constant multiple rule. So we have derivative of this part is simply equal to 4. Okay? Now, keeping x fixed. So this time, for the second part, so we keep x as fixed or x as constant, and then we differentiate with respect to y. So we will use this notation, or the second notation here. Okay, so for this part, we have partial derivative of the function of x and y with respect to y is equal to the derivative of the given function of two variables with respect to y. So equal to, so take note that here we treat x as constant. Okay, so for this part, we treat x as constant. Okay, I'll just abbreviate this class. We treat this as constant. So here at above, we treat y as constant here. Okay, so treating treating x as constant. So 2 and x cubed, they are constant. So we'll just take the derivative of y squared. Okay, so when you take the derivative of y squared, so we use the power formula. Okay, so using the power formula, so this becomes 2y. Okay, after that, you multiplied it by the rest of the term. So we have 2x cubed times 2y, so 2 times 2 is 4. So this becomes 4x cubed y. So that's why we have here 4x cubed y. Then derivative of 2y with respect to y. So we have 2. Derivative of 4x. 4 is constant. X is treated as constant. So this becomes constant. The product here becomes constant. So derivative of constant is equal to 0. That's why we have only this part here. Then after that, substitute the values. So using this, okay, so using this result, then substitute the value for x and y here. Okay, so our x and y is given us here. So this is our x. Okay, this is our x value. So when you take the partial derivative with respect to x, okay, so that's the same for this part here. Okay, so they're just the same. So substituting the value here, so 6 times x squared, so 1 squared times y squared. So our y is 3, so 3 squared plus 4. So plus 4. So when you evaluate this, it gives us 58. Okay? Then similarly, for the second part, so partial derivative of the function with respect to y at this point, coordinates 1 and 3. So substituting 4 times, this is 4x cubed, so 1 cube. So x is 1, 1 cube, so equal to 1 times 4, so equal to 4. Then times y is 3, so times 3. So this becomes 4 times 1 cube is 4, times 3 is 12, plus 2 is 14. Okay, so this agrees with our result in our example number 1. Okay, so they're just the same. So that's another way of solving this problem class. Alright, now let's proceed to example number 3. But before we go to that number, so let us have this principle first. So we have here the partial derivative notations. If z is a function of x and y, then the partial derivatives represented by this notation f of x and f of y are also denoted by the following symbols. So these are just the same as partial derivative of f with respect to x, or partial derivative of z with respect to x. So this is for one part. Okay, so this represent this one. Okay, so they're just the same. And the other one, partial derivative of the function or f with respect to y, or partial derivative of z with respect to y. So this is equivalent to this part here. So they have the same meaning. Okay, now some typical notations for the partial derivatives of z as a function of x and y at a point x sub 0, y sub 0 are also denoted or given in this expression. Okay, so this is similar to this one here, but this gives us additional. Then you have the bar here. So it indicates that we're so specific, the partial derivative of the function with respect to x at this particular point with these coordinates. Or this is equivalent to this one. Now we're specific, no? We are given a specific point here, x sub coordinates x sub 0, y sub 0. So in other words, they are just this one here is so all of this, represent this part here. So this indicates, so this notations here is the same meaning as this one at a specific point, x sub 0, y sub 0. Or if you are going to find the partial derivative of the given function with respect to y, so you just change this to y with respect to y. So just change x here is as into y here. Okay, to give you an equivalent for this. Okay, now the symbol, this symbol here, class, as you can see, this symbol here, this is called the partial derivative sign. Okay, this is the partial derivative sign. It is derived from the Cyrillic alphabet. So example number 3. Okay, so example number 3, find the partial derivative of z with respect to x and the partial derivative of z with respect to y if z is equal to x to the fourth times y times sine x times y cubed. Okay, so our solution here, you take the partial derivative on both sides. So taking the partial derivative on the left side with respect to x, so this is the result, and taking the derivative, the partial derivative on the right side of the equation, so we have this result. And this is the same as here we use the uh, product rule. So we have the product rule in our previous formula. We have the derivative of u times v with respect to x. Okay, this is equivalent to, I hope you can still remember, class. So this is equivalent to u times the derivative of v with respect to x plus v times the derivative of u with respect to x. So we will still use this formula, but this time we have to use the partial derivative sign. So instead of using d and d here, so we use this formula, class. The partial derivative of the product of u and v with respect to x is equal to u times the partial derivative of v with respect to x, then plus v times the partial derivative of u with respect to x. Okay, then apply your what you have learned in the rules and of differentiation. So in this case, we have sine a function here is given, so you just use the formula, no, for the derivative of the trigonometric functions. Okay, so in this case, so we just defined what is our u, what is our v. So in this case, so this is our u, right, and this is our v. Okay, so this is equal to, so this is our u times the derivative, no, partial derivative of u, so our sorry, v. So this is our v, partial derivative with respect to x, plus v times the partial derivative of u with respect to x. So we are now following this formula for this first line of our solution. Okay, then applying the formula for the derivative of sine. So the derivative of sine is cosine. So that's why we have here, we just copy x to the fourth. This is our u. Then the derivative of this one, so we use partial derivative. So using the rules in differentiation, derivative of sine is cosine. So that's why we have here cosine. And then it's something like this, class. The derivative of sine u, okay, derivative of sine u with respect to x is equal to cosine. This is cosine u times the derivative of u with respect to x. Okay. Now we are using the partial derivative, so you use here partial derivative of sine u with respect to x. Okay, with respect to x is equal to cosine u times the partial derivative of u with respect to x. Okay, so in this case, when you use this formula, so this is now your another u. So this part, so this is your u. So since you are differentiating with respect to x, so you held y as constant. Okay, so that's why you have only here y cubed, because you held x as constant. Sorry, you held y as constant. So you're differentiating. So it's something like this, class. The partial derivative of u, where our u is x y cubed. Okay, y cubed. This is y cubed with respect to x. So now we're differentiating with respect to x. So it means that y is constant. Okay, so this is constant. So we treat this as constant. Okay, so this is constant. So therefore, we just take the derivative of x. So derivative of x with respect to x is equal to 1. So that's why the result is we have only 1 here, y. Because the derivative of x with respect to x is equal to 1. 1 times y cubed. So we have here y cubed. And so on and so forth. Okay, anyway, this is the details of this one is shown in the third example class in our part 3 of our discussion. All right, so in our solution, the detailed solution of this example, in the next video, there's a little discrepancy which I'm going to indicate, just the notation class. Okay, so in that video, I put d only here, dx, also dx here, but it should be the partial derivative. Okay, just take note that this should be the symbol that we use in the denominator in that video, and so with this also. Okay, so I think that's all for this part, and I hope you see the details of the solution. And this is the details of the solution, class. And in the next video, you will see how, the step-by-step process of solving example number 3. Okay, thank you very much, and I hope that you will also watch the detailed solution for example number 3. Thank you very much, and see you in the next video. Bye.